Experiment 2. To find the wavelength of monochromatic light using Newton's ring apparatus. The phenomena of Newton's ring is named after Isaac Newton. It is an interference pattern caused by reflection of light between two surfaces, a spherical surface and a flat surface. Main components of Newton's ring apparatus. Sodium lamp, which gives yellow light. The wavelength of this light corresponds to 5893 angstrom, and we are going to find the wavelength of sodium light based on interference. Traveling microscope. Traveling microscope is used for two purposes. One for viewing the interference pattern and also for computing the diameters of the ring. And for computing the diameters of this ring, we have two screw gauges. One screw gauge is meant for moving the microscope towards left or right, and other one is used for moving the microscope towards front or back. We can use any one for determining the diameters of the observed fringe pattern. A plano-convex lens of large radius of curvature is kept on top of an optically plane glass plate. This is the arrangement of lens and glass plate. The flat face of the lens facing up and the curved face in contact with the plain glass plate. A transparent glass plate inclined at 45 degree, which turns the light rays coming from the source through 90 degree so that rays fall normally on the plano-convex lens. So summarizing the setup of the Newton's ring, we have a monochromatic light source, lens glass plate combination, a 45 degree glass plate, and a microscope for viewing the interference pattern. When monochromatic light is made to fall on the lens glass plate arrangement, the light reflected from the bottom surface of the lens and light reflected from the top surface of the glass plate will interfere with each other to produce interference pattern, which we can view with the help of the microscope. A plano-convex lens of large radius of curvature is kept on top of an optically plane glass plate. So due to this arrangement, a variable size air film is formed between the lens and the glass plate. The thickness of the air film at the point of contact is equal to 0, and the thickness increases from the point of contact towards the edge of the arrangement, and thickness is same along the circumference of a circle. When a parallel beam of monochromatic light is made to fall on the lens glass plate arrangement, a part of it is reflected from the bottom surface of the lens, and the transmitted one is again reflected from the top surface of the glass plate. These two reflected light interfere with each other to produce interference pattern. This is the interference pattern that we see through the microscope. At the center, we have a spot which is called the central dark spot. Surrounding the central dark spot is the first bright ring, then the first dark ring, then a second bright ring, second dark ring, third bright ring, third dark ring, and so on. We can see that as the order increases, the rings are getting crowded. Interference depends on path difference. Now we are going to calculate the path difference of ray 1 and 2. That is a ray that is reflected from the bottom surface of the lens and a ray that is reflected from the top surface of the glass plate. Now let the thickness of the air film at this point be T. Now from theory of interference of thin film, we have the optical path difference equal to 2 mu T cos R. We know the media between lens and glass plate is air and R equal to 0 for normal incidence. Therefore, the expression for path difference become path difference equal to 2T, mu equal to 1 for air and cos r equal to 1 for normal incidence. So the path difference between 1 and 2 equal to 2t. But when you observe the reflecting boundary or reflecting interface, the first reflecting boundary is a denser, rarer interface, and the second reflecting boundary is rarer, denser interface. If light is reflecting from a rarer, denser interface, the reflected light will suffer a path change or phase change. So the reflection at air glass interface is accompanied with a path change, which is of lambda by 2. Taking into account the phase change that happens to reflection, the optical path difference become t, which is the distance traveled by ray 2 down, plus lambda by 2 is a path change due to rarer denser interface reflection, then t up. So the total path difference become 2t plus lambda by 2. Condition for maximum. Equate the path difference to the general condition of maxima. That is, general condition of maxima is n lambda. So equate the path difference to n lambda, we get the condition for constructive interference. That is 2t plus lambda by 2 equal to n lambda. Or simplifying, we get 2t equal to n minus half lambda. And condition for destructive interference or minima intensity is 2t plus lambda by 2 equal to 2n plus 1 lambda by 2, equating the path difference to general condition for minima. Simplifying, we get 2t is equal to n lambda. That is, light reflecting from the point where the thickness is t can interfere either in a constructive way or destructive way. Whatever it be, if the thickness is favoring maxima intensity, and this condition will be satisfied by a set of points which lie on a circle. The thickness is favoring minima intensity, then this particular condition will be satisfied by a set of points which lie on a circle. So the interference pattern is concentric circular rings which are alternatively dark and bright. At the center, we have a dark spot. From the expression for maximum and minimum, we understand that if we know the thickness of the air film, then we can find wavelength of the monochromatic light. But it is very difficult to measure thickness. But the measurement of thickness can be done by measuring the diameter of the observed ring pattern. With the help of the microscope, we can measure the diameter of the ring. So the difficulty in measuring t is simplified to determining the diameters of the ring. If t is the thickness of the film corresponding to nth dark ring of radius Rn, or the radius of curvature of plano-convex lens, applying Pythagoras theorem, we can write r square is equal to Rn square plus r minus t the whole square. Expanding r minus t the whole square, we can write r square is equal to Rn square plus r square minus 2rt plus t square. Neglecting t square, because thickness is a very small value, on simplifying we can write t equal to Rn square divided by 2r, or Rn square is equal to 2rt. Rn square is equal to 2rt. Replacing 2t by minima condition is 2t is equal to n lambda. We can write Rn as Rn square is equal to nr lambda, or Rn is equal to root of nr lambda. Diameter is twice radius. So we can write the expression for diameter as diameter of the nth dark ring is equal to root of 4r n lambda. Similarly, if we express 2t as n minus half lambda, that the condition for maximum, we get Rn equal to root of n minus half r lambda, or diameter of the nth bright ring is equal to root of 4r n minus half lambda. That is, dark and bright ring expression dn is equal to root of 4r n lambda. Bright ring diameter is root of 4r n minus half lambda. R is the radius of the plano convex lens, n is the order, and lambda is the wavelength. Let dn be the diameter of the nth dark ring and dm plus n be the diameter of the m plus nth dark ring. We can write dn square is equal to 4r n lambda and dm plus n square is equal to 4r m plus n lambda, where r is the radius of curvature of the plano convex lens. Equation 2 minus equation 1 gives dm plus n square minus dn square is equal to 4r m plus n lambda minus 4r n lambda. Simplifying, we get dm plus n square minus dn square is equal to 4r m lambda, or lambda equal to dm plus n square minus dn square divided by 4rm. Therefore, the determination of wavelength have now reduced to determination of diameter. The diameter can be measured from the observed fringe pattern, and knowing the radius of curvature of the plano convex lens, we can find the wavelength of the monochromatic light. To find the wavelength of monochromatic light using Newton's ring apparatus, we use the formula lambda equal to dm plus n square minus dn square divided by 4rm. Screw gauge has two scales. One is called the pitch scale, the other one is called head scale. Pitch scale is in millimeter, and head scale there are 50 divisions. If you observe the pitch scale of the screw gauge, 10 division is equivalent to 5 millimeter, or 1 division is equal to 0.5 mm, or 1 pitch is equal to 0.5 mm. And the head scale there are 50 division, so the least count of the screw gauge is 1 pitch divided by number of division on the head scale, that is n, which is equal to 0.01 mm. Focus the microscope so that we get clear interference pattern. Now turn the screw gauge and make the crosswire coinciding with the central dark spot. Now turn the microscope towards left by working the screw gauge and make the vertical crosswire tangential to the 20th dark ring on left side and note the reading. Now we are going to turn the microscope towards right. While turning towards right, make the vertical crosswire tangential to the 18th dark ring on the left side and the corresponding reading is noted. Turn the microscope towards right. Make the vertical crosswire tangential to the 16th dark ring and the corresponding reading is noted. Note the reading corresponding to the 14th dark ring. Note the reading corresponding to 12th dark ring. Note the reading corresponding to the 10th dark ring. Reading corresponding to the 8th dark ring. Now take the reading corresponding to 6, 4 and 2nd dark ring on left side. Cross the center. Take the reading corresponding to the dark ring on right side. Take the reading corresponding to 4th dark ring on right side. Take the reading corresponding to 6th dark ring on right side. Take the reading corresponding to 8th dark ring on right side. Continue. Take the reading corresponding to the 18th dark ring on right side. Take the reading corresponding to the 20th dark ring on right side. To find the diameter of the ring, we take the difference of two readings, that is microscope reading on left side minus microscope reading on right side gives the diameter of the ring. For example, to calculate the diameter of the 20th dark ring, microscope reading corresponding to left 20 minus microscope reading corresponding to right 20 gives the diameter of the 20th dark ring. Now we are going to tabulate the observation for wavelength measurement. What we do is we turn the microscope towards left and make the vertical crosswire tangential to the 20th dark ring on left side. Now when the vertical crosswire is tangential to the 20th dark ring on left side, the screw gauge view is like this. Now what we do is we pick out the pitch scale reading and head scale reading and note the values. Now the pitch scale and head scale reading corresponding to left 20 reading is pitch scale is 5 and head scale reading is 7. Now we calculate the total reading using the formula total reading is equal to PSR plus HSR into LC. So we get the reading as 5.07. When you tabulate right reading, the first reading should be written down, then the reading corresponding to fourth, then reading corresponding to sixth, and reading corresponding to 8 and so on as indicated by the red arrow. Sample reading. Now we have the reading of left side and right side. Calculate the total reading using the formula. Total reading is equal to PSR plus HSR into LC. Then find the diameter. Then find the squares of the diameter. The last column. D20 square minus D10 square. D18 square minus D8 square. D16 square minus D6 square. D14 square minus D4 square. And D12 square minus D2 square. Find the average. The radius of curvature of the plano-convex lens R equal to 44 cm and M equal to 10. Compute wavelength using the formula lambda equal to dm plus n square minus dn square divided by 4 Rm. On substituting the values, we get the value of wavelength of the monochromatic light.